Today we'll talk about the DC motor drives, and before going to the drives that can be used to control the DC motors, we'll make some revision for the DC motors, how DC motors work, and we'll study two types of DC motors which are well known now, and then after that we'll go for the drives that can be used to drive this kind of motors. Okay, when you talk about the DC motor, you'll find that these kind of motors are used extensively in variable speed drives. And also you'll find that there are a few advantages for these DC motors. Some of the advantages is that we can provide speed control over a wide range of operations. And also you'll find that the starting torque for this kind of motors is high compared to other motors, and they are used extensively in industry and in toys, in many applications. If you look at the disadvantages, you'll find that we have the maintenance cost, and because you'll find that we need to change brushes and commutators. This kind of motors, it cannot last for longer time, so the reliability, it's a question here. But it's not a problem. The motor itself, like similar to the transformer is kind of device that can last for many years. Okay, it's a very reliable. Similarly, the motor, same thing, because it's just coil, core, and that's it. Okay, the only problem here is that we have maintenance cost for brushes and commutators. If you look at the DC motor itself, you'll find that we have two types of DC motors. It depends on the circuit that is operating this motor. Okay, one which is well known, which is called what? The separately excited DC motor. And the other one is the series excited DC motor. Today we'll study the separately excited DC motor. But before going to this, let's have a look at the DC motor itself and see how the DC motor works. Just some revision for what we have studied before. Now, usually we have two parts in the motor. We have something called the rotor, which is this part, okay, which is in the middle here. This part is expected to be rotating, and we have a stator, which is fixed part. This rotating part, it's called armature, and the fixed part is the which is the stator, is the field circuit. Okay, what we care about here is you need to understand that the motor is something like we have coils within the motor, within the rotor. Okay, we have coils within the rotor or the armature, and we need to apply field, magnetic field to be applied on this armature. Okay, so what we do actually is we have two circuits. The circuit number one, which is fixed, will have magnetic field in this from north to south in this direction. So this is number one. Number two, we have another circuit or another part of this motor, which is this part. It has current flowing in this direction through the brushes, and then it will go to the coil and will go in this direction, away. It will go away or inside the paper, and then this will go there and will be connected and then will come towards you. Now, once we have current and we have magnetic field from left to right, you'll find that at this point we have force applied in this direction. Similarly, it will happen in the opposite side. On the right side here, we have magnetic field to the right, we have current coming towards you, then you will find that we have force in this direction. Okay, and then the motor will rotate. If you have force in this direction, up and down, then the motor will be rotating, and so on and so forth. Once this point move to this direction, you will find that the current through the coil, it became the opposite side, and it will be always on the left side here away from you, and on the right side it will be always towards you, and the force will be all the time here up and here down, and the motor will keep rotating. This is the simplest way to design a motor. This is a DC motor. Of course, here we repeat the same thing, but for the opposite side. Now, when we said this, let's say this is point A, for example, and this is point B. Point A moved here, and point B moved here. Then you'll find the current at point B also going away from you, and then the current, as we said, on this direction, on this part, you'll find it always away from you, and the force will be always down. And here the same thing, the current will be towards you, and always the force will be always up. Okay, and the motor keeps rotating. So here we understand we have two parts in a motor. We have the rotating part and we have the fixed part. The fixed part has the magnetic field. So we expect that with there is a circuit in a separately excited motor, there is a circuit, and this circuit is called the field circuit, which generates the magnetic field and which is separated from the armature circuit. Now let's move and study the separately excited DC motor. For the separately excited DC motor, you'll find that, as we said, we have two parts. One part is the armature circuit and the other part is the field circuit, which is the fixed circuit. This example, you'll find it very popular because of many reasons. Number one, it contains three parts of subjects, like you'll find electric circuits, you'll find control systems, right? If you remember, in control systems, we studied something like this. You'll find that we'll use it in machines, we can use it in power electronics and drives. We studied this circuit in control systems because we were interested in analyzing the mechanical part and see how we can derive the transfer function in a mechanical rotating mechanical system. Today we are studying this circuit because we are interested in driving the motor. Okay, we are interested in designing the DC motor drive. So we need to analyze this circuit and see how we can obtain the relationship for the armature circuit and the field circuit and so on and so forth. Let's see, we'll just make some revision. We said, okay, when the motor is excited by a field current and the armature current IA flows in the armature circuit, the motor develops a back electromotive force and a torque to balance the load at a particular speed. So once we applied current here, you'll find that we have electromotive force here on the motor, and also we have developed torque in this direction with a specific speed, as shown here. And this developed torque must be equal to all forces, all torques on this direction. So the field current is independent of the armature current, and the changes in the armature currents has no effect on the field current, which is known because this is a separately excited motor, and normally the field current is much less than the armature current. What we care about here is this torque, the developed torque, must be equal to the torque that is developed from the motor, must be equal to these forces, or not forces now, they are torques, right? The load torque, the torque that's coming from the friction, and from the inertia. Just some analysis for the circuit. You'll find the voltage here, Vf is equal to how much? Vf is equal to the voltage across the inductor and the voltage across the resistor. So you'll find this is equal to Rf IF plus LF, which is the field inductance, dIF by dt. So the voltage here is equal to this voltage and this voltage. This is very simple. Now, if you look at the armature circuit, you'll find also the voltage here, the armature voltage, is equal to how much? The voltage on the resistor, the voltage on the inductor, and also the electromotive force. So VA here is equal to how much? RAIA, the armature current, plus LA DIA by dt plus EG. Now we need to find a relation between the rotating part and the electrical part, the mechanical part and the electrical part. And this relation is usually defined by two equations. Equation number one, the relation between the electromotive force, which is related to the torque. So the electromotive force and the field current, because we agreed that here we have field separately excited from the field circuit. So this will be equal to how much? EG is equal to how much? KV times the speed times the field current. So this is the relation between the electromotive force and the field current. We have also another relation, which is the developed torque TD is equal to how much? This constant KT times IF times IA. Now we agreed that this developed torque is equal to how much? Is equal to all these torques. So this will be equal to how much? The developed torque TD is equal to J d omega by dt plus B times omega plus torque, the load torque. Now we'll go for all these definitions one by one. Now, so omega is the angular speed. So this makes our life easier to make some definitions, which is radian per second. B from control systems is what? Is the viscous friction constant, which is measured by Newton meter per radian per second, because this is the rotating one, right? And kV is what we call speed voltage constant, and it's measured by voltage per amperes radian per second. What else we have? Another constant KT, which is the torque constant, which is measured by Newton meter per amperes. Finally, we have LA, LF. These are simply what? The armature circuit inductance and the field circuit inductance. These are measured by Henry, and the armature circuit resistance RA and RF measured by ohms, right? And the torque TL, it's measured by what? By Newton meter. These are just summary for the units that can be used for these parameters. Why it's important? Sometimes you'll find that if you know the unit, you'll be able to find the relation, the equation that defines this parameter easily from the units. Or if you know the equation, you can guess the unit. Right? Sometimes we have more than one unit, but there are some few commonly used units, so we can just follow them and use them. Now, under steady state conditions, after the motor starts rotating, and after that, after like few seconds, you'll find that this motor reached to the steady state condition and the speed became constant. So the rate of change of the current at this moment is equal to how much? Is equal to 0, and the steady state average will be as follows. You'll find that VF is equal to how much? RF times IF. Why? If you come back to this equation, we say that VF is equal to how much? RF IF plus LF di by dt, right? Under the steady state condition, the rate of change of current is equal to how much? Is equal to 0. There is no change on the current, so this part will be 0, and VF is equal to how much? RF times IF. What else we have? Other equations. EG is equal to same thing, KV times omega times IF, and VA, again, the rate of change of the current is equal to 0, so the part will be equal to 0. So this will be RA times IA plus EG. Now EG is already defined here, so we can say that VA is equal to how much? RA times IA plus KV. KV is constant, omega times IF. So this is VA, the armature voltage. You'll find that there are two parameters can control the armature voltage here, the field current and the armature current. If you look at the developed torque, TD is equal to how much? At steady state condition, this is by definition is equal to how much? KT times IF times IA, and this also is equal to how much? From the previous equation, because you say the developed torque is equal to the all torques on the rotating part, the load torque, the friction, and the inertia, right? So any part that is related to rate of change of something, this will be equal to 0. So the speed is not changing at this moment. We said again, TD is equal to how much here? J d omega by dt. So this is the rate of change of the speed, the accelerating. So this will be deleted. At steady state, there's no change on the speed, right? Plus B omega plus TL. Now we had all these equations at the steady state conditions. So what we'll do is the following. So this will be 0. So TD is equal to B omega plus TL, right? From this, we can say that the developed power PD also is equal to how much? The developed torque times omega times the speed. So this is given here, the power omega times the torque. Now let's have a look at some relationships here. We want to draw the relation between EG and the IF. Okay, EG IF. If you look at this equation, you'll find that EG is equal to constant speed times IF. So we expect that the relation to be linear. Okay, no problems, it will be linear. But at some point here you'll find that we have saturation. Then this will go to be constant. Why? This is because similar to the transformer. The transformer is as if we have housing. So we have saturation for the magnetics, for the magnetic field, right? So this is due to the magnetizing effect. So you'll find that the region here is linear, but after some point you'll find that we have saturation due to the magnetic field saturation, because the motor has a limited number of coils, a limited number of magnetics. We cannot transfer infinity magnetic field within the transformer, right? And the transformer and the motor have similar idea, same thing here. So this is approximately, we have a linear region, no problems. Then after some point we have saturation. If you want to draw the relation between the speed and the torque and power, you'll find at the beginning here we have constant torque, and then the power is increasing. At some point here, when we reach to the rated speed, so some modification must be applied. You'll find the power is constant, the rated power here, constant, PD, and then the torque, developed torque, at the beginning, the torque is high, and after, when the motor starts moving and reach to the steady state condition, then of course the torque will be smaller. So this is the torque. TD. If you look at the current IF and IA in the separately excited motor, you'll find that IA is constant. This is IA. By the way, IA is directly related to the torque. If you want to increase the torque, you keep IA constant, or you control IA, the armature current. Okay, so the current is directly related to the torque. This is the key point here. And if you look at the field current, you'll find that the field current is constant here, and then after that this can be decreased to compensate and make sure that the power, the developed power, is constant. So this is IF, this is IA, the armature current. Here we have the developed torque and the developed power, and we can say that here we have, of course, let's say this is the constant torque region, and here we have constant power region, because we cannot increase the power all the time. The motor will, you cannot just keep increasing the speed of the motor, right? We have to reach at a rated speed, at steady state speed, right? Now let's say this equation here, VA equation, I would say this equation is star, equation number star, and from this equation star, we need to find the speed, omega. So from this equation, omega is equal to how much? Here we have RA IA plus EG. Okay, we have VA, so we can say VA minus RA IA over KV. So take this one on the other side, right? So this will be VA minus RA IA over KVIF. So this is the speed, omega, right? We can replace IF with what? With the voltage VF over RF from this equation, because we said after a certain point we have a steady state condition, and the voltage VF is equal to how much? RF times IF. So we can say omega is equal to how much? VA minus RAIA over KV times VF over RF. This is the speed. Looking at this equation, we can conclude that we can control the speed, or we can change the speed by many ways. Number one, we can change the speed by what? By controlling VA. If you control VA, change the value of the armature voltage, we can change the value of the speed. we can change the speed of the motor, right? So number one, how we can control with the voltage, with the speed. Number one, we can control VA, the armature voltage, and that's what we call the voltage control. Voltage control, okay? Okay. Number two, we can change the field current, IF, field control. Okay, so this is field control. Okay, we have the armature circuit, everything is there. If we change the armature current, okay, that is applied separately on the motor, we can change the speed of the motor. Number three, we can change the armature current, or what we call the torque demand. So at constant IF, we can change IA, the armature current, and we said IA is directly linked with the torque, right? IA and the torque like linked to each other. So once we change IA, we will be able to change the torque, right? So that's what we call a torque demand. So these are the three ways to control the speed of a DC motor. We know the relationships here between the torque and the speed, power and the speed, and then also the armature current, the field current, and the speed over a constant power or constant torque condition. Now let's have a look at one example, okay, one simple example, and try to solve it. It's just a straightforward example, not difficult, and then see what we can do. The example says we have a 15 horsepower, 220 volt, 2000 revolution per minute, RPM, separately excited DC motors, controls a load requiring a torque of 45 Newton meter. Okay, so here we have the load torque is 45 Newton meter at a speed of 1200 RPM. So the information here, the first one, these are the rated information here, the rated specification of the motor. So this motor controls what? A load 45 Newton meter at 1200 speed. So expect that we have operating condition which is below the rated conditions. The field circuit resistance is 147 ohms. The armature circuit is 0.25 ohms, and the speed voltage constant of the motor and torque constant is equal to how much? 0.7032 volt per ampere radian per second. So here we have the same voltage for the constant kV and kT, and then he says, okay, the field voltage is 220 volt. Okay, the versus friction is negligible, so B is 0, and the armature current may be assumed continuous and ripple free. What we need to do is to find the back EMF, e.g., the required armature voltage VA, and the rated armature current of the motor. Now let's summarize the information that we have first. So we can say RF is equal to how much? 147 ohms, RA 0.25 ohms, KV and KT is equal to how much? 0.7032 volt per amperes radian per second. What else we have? VF is equal to how much? This is given 220 volt, and the developed torque and the load torque is equal to 45 Newton meter, because the friction is 0, so nothing there except the load, which is 45 Newton meter. This is the load torque and the developed torque. So these are the general information. Now the speed is given by how much? The speed is 1200 RPM, but we need this speed in radian per second. How to convert this one to radian per second? So here we have 1200 revolution per minute, right? Now a minute, how many seconds? Minute is equal to how much? 60 seconds. So we can say minute over 60 seconds, as if we changed nothing. Then we can say, okay, we need something to get rid of the revolution, so we can say this is 2 pi radian per 1 revolution. This also as if we have changed nothing, because 1 revolution is equal to how much? 2 pi radian. So what we do, minute goes with minute, revolution goes with revolution, then we left with 1200 times 2 pi radian per 60 second, right? So here this will be 1200 times pi over 30 radian per second. Multiply, so omega is equal to how much at this point? It will be 125.66 radian per second. So this is the speed in radian per second. Now everything is there. We need to find the requirements. We need to back EMF, EG. EG is equal to how much? KV, which is given, speed omega times IF. IF is equal to how much? VF over RF. So IF is equal to 220 over RF, which is 147. So IF is equal to 1.497 amperes. We can just use this one. We have omega, we have kV, we have IF, so we can simply substitute by this and get the EG. So kV how much? 0.7032, right? Times omega, which is 125.66 times 1.497 amperes. All these must be equal to how much? 132.28 volts. So this is the electromotive force that is applied on the motor itself. Now the second requirement is we need to find the required armature voltage VA from the circuit. So we can say that VA, now we need to find VA. So we can say that VA is equal to how much? RA times IA plus the electromotive force EG. Now we have RA, we need to find what? We need to find IA. We don't know the value of IA, right? This is not given in the question, so we need to bring it. So we can say that IA, okay, is related to the torque, to the developed torque, right? So directly we can find this from the developed torque. So TD is equal to how much? KT times IF times IA, right? So IA is equal to the developed torque over KTIF, and the developed torque is 45 over KT is given 0.7 something, 032, and IF is equal to how much? 1.497. We just brought it in the in section A. Just multiply this, you'll find IA is equal to how much? 42.75 amperes. And if you look at the difference here, as we said in the previously, IF is usually much smaller than IA. Okay, IA is very large compared to IF in the separately excited motor. In the series excited motor, you'll find that IA and IF are same value because they are in series, so we have the same circuit for the IF and IA. So we got IA times RA plus EG, we can find VA, so simply we can say VA is equal to how much? RA, which is 0.25, times IA, which is 42.75 here, plus EG, which is from section A, requirement A, so 132.28 volt. So all these will be how much? VA is equal to how much? 142.97 volts. So this is VA. Now the last requirement in this question says please find the rated armature current of the motor. So we need to find the rated current, the rated armature current of the motor. Now how to find the rated armature current for the motor? From the rated values that are given at the beginning of the question. Okay, not the operating conditions, not the 1200. Now this 1200 RPM brought the IA, the operating current, not the rated current. The rated current can be obtained from the first line of the question. So we can say that C, we need to find the power rated is equal to how much? The rated voltage times the rated current. So if you find the rated, we need to rate the rated current, so this will be rated power over the rated voltage. But before this, we need to find the rated power. The rated power is given by how much? By in horsepower. So we know that 1 horsepower is equal to how much? 7046 watt, right? So we need to make this conversion. So we can say I rated is equal to how much? The rated power, we said 15 horsepower, so 15 times 746, this is in watt. And we have the rated voltage, which is how much? 220. If you calculate this, so this will be 50.864 amperes. So this is the rated armature current. If you look at the operating armature current is how much? 42. Because it's working at the lower RPM. At 2000 RPM, it will be 50 amperes. Okay, and of course the torque at this point will be higher. So this is a very simple example. Okay, just direct application to the equations and the definitions that we have just obtained on the separately excited motor. The key point is that we need to understand the relation between the current, armature current, field current, and the power and the torque. These are very important. I hope that you enjoyed this lecture, and I will see you in the next lecture.